Hello, in this video we're going to talk about the generic cubic equation of state. In a previous video we talked about van der Waals equation of state and the compressibility factor Z. In this video we will mention both of those as well as use the compressibility factor Z to find the cubic polynomial expression using the generic cubic equation of state. So van der Waals equation of state is pressure equals the gas constant R times temperature divided by the specific volume minus the parameter B minus the parameter A divided by the specific volume squared. So van der Waals has the parameters A and B. The parameter A is the attraction between the molecules, and then the parameter B is the excluded volume because of the space between the molecules. So after van der Waals equation, many people wanted to improve upon this equation, and so there came the generic cubic equation of state, which is pressure equals the gas constant R times temperature divided by the specific volume minus the parameter B minus the parameter A of T divided by the quantity of the specific volume plus epsilon B times the quantity of the specific volume plus sigma B. So some changes that we should know is this T here. It was experimentally found that the temperature affects the attraction parameter, and so they added in that it is temperature based, and then also the added values of epsilon and sigma B. So if we take a look down here, we have the table for many different equations of states and the parameters. So we can see that there is the van der Waals equation as well as an SRK, a PR. And so if we go back up here, it talks about these people who went into developing more accurate versions of van der Waals equations, and a lot of these equations like the SRK and the PR is what you see nowadays because again it is more accurate than van der Waals. But so let's just take a look at van der Waals up here. We have that the A of T is 1 and the sigma and epsilon is 0. So if we were to put in 1 for this value here and then cancel out the epsilon and the sigma with 0, we would get A over V squared, which is exactly what we have in van der Waals equation. So it shows that van der Waals equation also follows the cubic equation of state, it just has different parameters. But so what we want to do in this video is we want to find the cubic polynomial expression. And so no matter which equation of state, whether you're using SRK or PR or van der Waals, it is to find the pressure at a given temperature and a given volume. But when we find the polynomial expression, we want to do it in terms of the compressibility factor. So the compressibility factor is derived from the ideal gas law, which is the pressure times the specific volume equal to the gas constant R times the temperature times, normally it would be moles, but we're assuming that the specific volume is per 1 mole, so that can omit the N. And so we know that the compressibility factor is the pressure times the volume divided by the gas constant R times temperature. And so we want to find the polynomial expression in terms of Z, the compressibility factor, using the cubic equation of state. So if we were to rewrite the generic cubic equation of state, we would get the pressure equals gas constant R times temperature divided by the specific volume minus the parameter B minus A. And normally the parameter A is based on temperature, but since we're not trying to find a pressure, we're just trying to find the cubic polynomial expression. The temperature is not as significant here, so we're just going to keep it as the parameter A. and we're going to divide that by the quantity of the specific volume plus epsilon b times the quantity of the specific volume plus sigma b. So I want this in terms of the compressibility factor Z. So in order to do that, I want to get this pressure on the left side here to be the same as the compressibility factor Z. So in order to do that, what I'm going to do is I'm going to multiply by the specific volume divided by the gas constant R times temperature. So if I were to do that, I would get pressure times the specific volume divided by gas constant R times temperature on the left. And then on the right, I can see that this in the numerator of this term is going to cancel out with the gas constant R and temperature times temperature in the denominator. And so I'm going to be left with the specific volume divided by the specific volume minus the parameter b, and then in this next term I'm going to have the parameter a times the specific volume divided by the gas constant R times temperature times the quantity of the specific volume plus epsilon b times the quantity of the specific volume plus sigma b. So what I'm going to want to do next is simplify this as best I can. So I'm going to substitute in Z, the compressibility factor, and then I'm also going to divide by this specific volume. So what I essentially am aiming to do is to get rid of this volume and this volume and this specific volume and these specific volumes. So in order to do that, I'm going to first sub in Z, so I get Z. And then so this is going to be divided by the specific volume, which is going to leave me with 1. This term right here, this quantity, will also be divided by the specific volume. So I'm going to be left with 1 minus B over the specific volume. Minus, this will, let's take a look at the denominator of this term first. So if I were to divide once by the specific volume, I would be left with the gas constant R times temperature, and then the specific volume, this quantity right here, divided by the specific volume, I would be left with 1 plus epsilon B divided by the specific volume, and then I would have the specific volume plus sigma B. But again, I want to get rid of this specific volume that I circled here, so I'm going to divide by the specific volume twice. So then this quantity will also be 1 plus sigma B over the specific volume. And so up here, since I divided the denominator by the specific volume twice, I will divide the numerator by the specific volume twice. So I would get A divided by the specific volume. So I'm just going to move that down into the numerator. So I'm going to be left with the compressibility factor Z equals 1 divided by 1 minus the parameter B over the specific volume minus the parameter A over the gas constant R times temperature times volume, the specific volume, times the quantity of 1 plus epsilon B divided by specific volume times the quantity of 1 plus sigma B divided by the specific volume. So as we can see, we have a pretty messy equation, but we're going to have to make it a little more messy before we clean it up. And the reason for that is because, as I mentioned earlier, we want the equation in terms of the compressibility factor Z and not in terms of the specific volume. So if we go back up here, we can move the compressibility factor equation around a bit to isolate the volume and get that the specific volume equals the compressibility factor times the gas constant R times temperature divided by pressure. And the reason we want to isolate the specific volume is so that we can substitute it into the equation. So we're going to substitute in V. And we're going to do this step by step so that we can see how we get to the next equation. So we're going to start at this V here. So if we have the parameter B divided by the specific volume, we're going to replace the specific volume with the gas constant R times temperature times the compressibility factor divided by the pressure. So this would be the same as multiplying it by the reciprocal, so we would be left with the parameter B times the pressure divided by the gas constant R times temperature times the compressibility factor. Moving on to the next V we have here, we are going to have the gas constant R times temperature times the compressibility, or times V, but in terms of the compressibility factor. So that's going to be the constant R times temperature times the compressibility factor divided by pressure. So that's going to give us the gas constant R squared times the temperature squared times the compressibility factor divided by the pressure. And then moving on to the next specific volume, we have that here. So what that's going to be is epsilon B divided by the gas constant R times temperature times the compressibility factor divided by pressure. We're going to move the pressure up because we're going to multiply by the reciprocal, so that's going to give us epsilon B times pressure divided by gas constant R times temperature times the compressibility factor. And then moving on to the last specific volume we have over here that we have to substitute in, we're going to have sigma B divided by the specific volume, so that's going to be divided by the gas constant R times temperature times the compressibility factor divided by pressure. Again, it's multiplying by the reciprocal, so that's going to give us the sigma B times pressure divided by the gas constant R times temperature times the compressibility factor. So now we are going to put all of this into the equation. So we're going to have the compressibility factor Z equals 1 divided by 1 minus the parameter B times pressure divided by gas constant R times temperature times the compressibility factor minus, we're going to have the parameter A divided by R squared times temperature squared times compressibility factor divided by pressure. We're going to real quick know that this is multiplied by the reciprocal, so we're going to move the pressure up to here with the parameter A. And then we're going to divide that whole thing by the quantity 1 plus epsilon B times pressure divided by gas constant R times temperature times compressibility factor Z times the quantity of 1 plus sigma B times the pressure divided by the gas constant R times temperature times the compressibility factor. So now that we've gotten rid of the specific volumes and everything is in terms of the compressibility factor, we're going to try to start cleaning up this equation. So to clean up this equation, we're going to use what we are given in this text here, and that is beta and Q. So beta and Q are defined as, so beta equals parameter B times pressure divided by gas constant R times temperature, and Q is defined as parameter A divided by the parameter B times gas constant R times temperature. And so let's just first start with beta and see where we can put beta in, like what we can substitute for beta. So we see here we have a B times pressure divided by gas constant R times temperature. Here we have a B times pressure divided by gas constant R times temperature. And here we have a B times pressure divided by gas constant R times temperature. So we know that we can put beta into those areas. So where can we use Q? Well, we don't really have anywhere that is directly equal to A divided by B times gas constant R times temperature, as we did with beta. But we do see that we have a super messy numerator of this term. So let's see if we could just try to simplify it, maybe using Q, maybe using beta, we're not sure yet. So we have the numerator is A times pressure divided by gas constant R squared times temperature squared times compressibility factor Z. Well, we see that Q has an A, and this messy numerator has an A. We see that it has a R, both have an R, both have a T. So we're going to take those out. And that leaves us with the pressure divided by a gas constant R times temperature times the compressibility factor Z. And we don't really have anything for this, but if we look at beta, we can see that there is a resemblance of the what we have. And so if we just take out what we have in common with beta, so we would have what we have in common with Q, which is A divided by gas constant R times temperature. And then what we have in common with beta is, well, the pressure is in both, and then gas constant R is in both, and temperature is in both. And so we are left with 1 over compressibility factor Z. And so what can we substitute in? Well, we know that beta equals B times pressure divided by gas constant R times temperature. But we don't have the beta here, so if we were to get rid of that, we don't have the B here, so if we were to get rid of that, we would get beta over B equals pressure divided by gas constant R over temperature. So we just moved this into the other side, and that's what we have here. So if we substitute that in, we have A divided by gas constant R times temperature times beta over B times the compressibility factor of 1 over Z, beta over B times 1 over the compressibility factor Z. Wait a minute, now, if we look at Q, it's A divided by B times gas constant R times temperature, which is what we have right here. So we can substitute that in for Q. So then what we would be left with is Q times beta divided by Z. So let's substitute these into the equation and see if it looks any cleaner. So we have the compressibility factor Z equals 1 divided by 1 minus beta over Z minus, up here we have QB divided by the compressibility factor Z, all divided by the quantity of 1 plus epsilon beta divided by Z, times the quantity of 1 plus the epsilon, or sigma beta divided by Z. And so what we're going to do is we're going to move this compressibility factor down to the denominator to clean up this numerator here. And so what we're going to have is the compressibility factor equals 1 divided by 1 minus beta over the compressibility factor minus Q times beta divided by the compressibility factor. And then we have 1 plus epsilon B divided by compressibility factor times the quantity of 1 plus sigma beta divided by the compressibility factor. So now that we have it pretty cleaned up with the compressibility factors and no specific volumes, as well as with Q and B, we're going to continue trying to simplify and clean this up as best we can by dividing by Z. So we're going to divide everything by the compressibility factor Z, and that's going to give us 1 equals 1 divided by z minus beta minus q beta divided by the quantity of z plus epsilon beta times the quantity of z plus sigma beta. So now what we're going to do is we're going to get like denominators and pretty much just expand this out into the cubic polynomial expression. So let's do this step by step. So if we multiply common denominators, we're going to have 1 equals z plus epsilon beta times the quantity of z plus sigma beta minus q beta times z minus beta, all divided by z minus beta times the quantity of z plus epsilon beta times the quantity of z plus sigma beta. And so now what we need to do is we're going to multiply everything by this denominator here to get rid of the denominator. So we will have z minus beta times the quantity of z plus epsilon beta times the quantity of z plus sigma beta equal to z plus epsilon beta times the quantity of z plus sigma beta minus q beta times z minus beta. So now what we're going to do is we are going to expand out our equations. So let's just start by expanding this group here. And so this is going to be compressibility factor squared plus sigma times beta times compressibility factor plus epsilon times beta times compressibility factor plus epsilon times sigma times beta. And we have to keep in mind that we are going to move this equation to the left side. And so all of these signs are going to be switched. So it's going to be negative compressibility factor squared minus sigma times beta times the compressibility factor minus epsilon times beta times the compressibility factor minus epsilon times sigma times beta. Now we can see if we move over to this group here that these two groups match these two groups. So we already know that this is going to equal compressibility factor squared plus sigma beta times compressibility factor plus epsilon times beta times compressibility factor plus epsilon times sigma times beta. Now the reason we don't use the negated negative values is because this is remaining on the right side, so we haven't moved it anywhere, so it's going to remain positive. So we're going to do this group multiplied by the group we have remaining on the left side, which is compressibility factor minus beta. Distributing that out, we're going to get compressibility factor cubed plus sigma times beta times compressibility factor squared plus epsilon times beta times compressibility factor squared plus epsilon times sigma times beta times compressibility factor, and that's going to, now we are going to move on to the negative beta, so that's going to be negative beta compressibility factor squared plus minus sigma times beta squared times compressibility factor. We're going to move that over slightly to give us some more room. And then we're going to get minus epsilon times beta squared times compressibility factor minus epsilon times sigma times beta. Now this last group that we have over here is going to give us q times beta, negative q times beta times compressibility factored plus q times beta squared. And again, we're going to move this to the left side. So everything's going to become the negative or the opposite sign. So it's going to be q times beta times compressively factored minus q times beta squared. Now what we're going to do is we're going to create a chart to help us organize all of these terms because there are quite a lot of them. So we're going to have compressibility factor z terms cubed. We're going to have compressibility factor z squared terms. We're going to have compressibility factor z terms, and then we're going to have constants. So we're going to go through and highlight them so that we can see where everything is. So for z cubed, we have just this factor there, that term. And then for compressibility factor z squared, we have this term, this term, this term, this term, and those are all the compressibility factor z terms. And then for just the compressibility factor z terms, we have, those are all for the z squared. So for just z, we have that term, this term, this term, this term, this term, and this term. And then the remaining ones are just constants, which means they do not have compressibility factor z. So now we are going to go in and write them all down. So for this one, we just have 1 for the compressibility factor z cubed. For the compressibility factor z squared, we have sigma beta, we have epsilon beta, we have negative beta, we have -1, and then for the compressibility factor z terms, we have epsilon sigma beta, we have negative sigma beta squared, we have negative epsilon beta squared, we have negative sigma beta, and then we have negative epsilon beta, and then we have q beta, and then for our constants we have negative epsilon sigma beta, and then we have negative epsilon sigma beta. This should be beta squared. So we have negative epsilon sigma beta squared, negative epsilon sigma beta, and then we have negative q beta squared. So to simplify a little bit, we can combine these two to be negative beta squared multiplied by sigma plus epsilon. We combine these two to be negative beta times sigma plus epsilon. And so if we were to put these all into one long polynomial, we would have z cubed plus sigma beta plus epsilon beta minus beta, I'm forgetting my compressibility factors. It would be compressibility factor z cubed plus sigma beta z squared plus epsilon beta compressibility factor squared minus beta compressibility factor squared minus compressibility factor squared plus epsilon sigma beta compressibility factor minus beta squared the compressibility factor times quantity of sigma plus epsilon minus beta compressibility factor times the quantity of sigma plus epsilon plus q beta compressibility factor z minus epsilon sigma beta squared minus epsilon sigma beta minus q beta squared. So that gives us our final polynomial for the cubic equation of state in terms of compressibility factor.